Section 3.2 is on angles and parallel lines. And you should recognize this diagram, or it should look familiar to what we talked about in the last section. We have two lines, L and M, that are cut by our transversal T. But in this case, line L is parallel to line M. When that happens, there become special relationships between the angle pairs, the angles in the angle pairs. Remember last time we talked about alternate interiors, so that would be like 3 and 5 and 4 and 6. Alternate exteriors, angles 1 and 7, 2 and 8. Consecutive interior angles, like 4 and 5 and 3 and 6. And then corresponding angles, so 1 and 5, 2 and 6, 3 and 7, and 4 and 8. All of those are our special angle pairs. Now, when the lines being cut by the transversal are parallel, a lot of really cool stuff happens. So our first thing here is we're going to talk about the corresponding angles postulate, which says that if parallel lines are cut by a transversal, then the corresponding angles are congruent. So since L is parallel to M and T is your transversal, then angle 1 is congruent to angle 5, angle 2 is congruent to angle 6, angle 3 is congruent to angle 7, and angle 4 is congruent to angle 8. And that's only if the lines are parallel. Using the corresponding angles postulate, we can then come up with the alternate interior angles theorem, which says that if parallel lines are cut by a transversal, then alternate interior angles are congruent. So let's go back to the picture. If L is parallel to M, then my alternate interiors, like angles 3 and 5, are congruent to each other, and angles 4 and 6 are congruent to each other. And that's the alternate interior angles theorem. We also have an alternate exterior angles theorem, which says that if parallel lines are cut by a transversal, then alternate exterior angles are congruent. So looking at our picture, if L is parallel to M, and T is our transversal, then angle 1 is congruent to angle 7. Those are alternate exterior angles, and they will be congruent. Angle 2 is congruent to angle 8, because those are also alternate exterior angles. And the last one here is the consecutive interior angles theorem. If parallel lines are cut by a transversal, then the consecutive interior angles are supplementary. They're not congruent to each other, they're going to be supplementary. So let's take a look at our picture here. If L and M are parallel and T is my transversal, then my consecutive interiors, so like 3 and 6, are going to be supplementary. You should be able to tell just by looking at them that they're not going to be congruent to each other, because in this case 6 is an acute angle because it's less than 90. 3 is an obtuse angle because it's greater than 90. So those are not going to be equal to each other, and the other thing that makes sense is they are supplementary. In the same way, on the other side of the transversal, angles 4 and 5 are consecutive interiors, and they are also supplementary. And just one note about the naming of these. The first one is a postulate, which means it's accepted to be true, it's not proven. And then actually we go ahead and can use that postulate to prove the other 3 theorems. I want to tell you about another theorem which is not official. I made this one up on my own. It's called Dietrich's theorem, and you cannot use it in a proof. You have to use the officially accepted ones. But this might help you to remember some of these things a little bit. Dietrich's theorem says that if parallel lines are cut by a transversal, then all of the acute angles are congruent to each other, all of the obtuse angles are congruent to each other, and any one acute plus one obtuse are supplementary. So let's take a look at that. All of the acute angles in this picture, 2, 6, 8, and 4. Well, you know 2 and 4 are going to be congruent because they're vertical. 6 and 8 are going to be congruent to each other. 2 and 6 are also corresponding angles, as are 4 and 8. Same thing is going to be true. All of the obtuse angles are congruent to each other. 1 and 3 and 5 and 7. And then if you take any one acute angle, say for example angle 2, and any obtuse angle, say for example angle 3, those are going to be supplementary. Then you can actually kind of work your way through and prove all of them that way. So again, you can't use Dietrich's theorem in a proof, but if it helps you to remember the other theorems, that would be really good. So let's, here's another theorem. The perpendicular transversal theorem. If a line is perpendicular to one of two parallel lines, then it is perpendicular to the other. So if L is parallel to M, and if T is perpendicular to L, then T is also going to be perpendicular to M. If the two lines are parallel, and the transversal is perpendicular to one of them, it has to be perpendicular to the other angle as well. And that's the perpendicular transversal theorem. And let's try a couple examples using a little algebra and our special angle pairs. So this says find the value of each variable and then explain how you did that. So we're given that the measure of angle 4 is 2x minus 17 and the measure of angle 1 is 85. So the first thing we want to do is take a look at our diagram and see what's going on here. Where's angle 1 and where's angle 4? Well, looking at this picture here, if angle 1 is 2x minus 7, angle 7 is also going to be the same thing because those are corresponding angles. Oh, I'm sorry, I got that wrong. If angle 1 is 85, my apologies. If angle 1 is 85, angle 7 must also be 85 since they are corresponding angles. And notice that angle 7 and angle 4 form a linear pair, so they have to be supplementary. So we can say the measure of angle 7 is also equal to 85 because it's a corresponding angle with angle 1, and the measure of angle 7 plus the measure of angle 4 has to equal 180 because they form a linear pair. So 85 plus 2x minus 17 equals 180. Or doing the subtraction, combining like terms and doing the subtraction, 2x is equal to 112 and x is equal to 56. Okay, and in terms of an explanation, I think it's fine that we can say that these are corresponding and that 1 and 7 are corresponding angles and 4 and 7 form a linear pair. So for example number 1, x equals 56. Let's take a look at example number 2 here. I'm going to give myself a little more room. Example number 2, the measure of angle 3 is 4y plus 30. The measure of angle 7 is 7y plus 6. So let's look at the diagram and see what's the relationship between angles 3 and 7. And this one's a little more straightforward. Those are actually alternate interior angles. And we know from our theorem that if the lines are parallel, cut by a transversal, alternate interior angles are going to be congruent. So 4y plus 30 equals 7y plus 6, or 3y equals 24, and y equals 8. So these are a couple examples of how you would use these special angle pairs in parallel lines cut by a transversal to solve some algebraic problems.